Yes,
Meeting
sir.
is being recorded. Started.
Yes, sir. Started.
I have started recording. Please go ahead.
Okay.
Okay, thank you, Kashif. Okay, so we will start. So very good morning, all of you. So today we have arranged one webinar on the introduction to finite element analysis using SolidWorks by resource person, Mr. Shivkant D. Tilekar, Senior Application Engineer, Simulation Based Engineering Aids and Consultancies Private Limited, Pune. So I request to our Honorable Dr. S.S. Wangikar, sir, to introduce today's guest. Thank you very much.
Okay. So very good morning to all. Am I audible?
Hi, sir.
Yes,
You are
sir, yes.
audible.
Okay. Very good morning to all. I take privilege to not only introduce but also welcome our today's speaker, eminent speaker, Mr. Shivkant Tilekar. So Shivkant Tilekar sir is acting as a passionate simulation specialist and SolidWorks elite in the best engineering aids and consultancies, Beacon. So he has completed his master's Tech from Design and Manufacturing from NIT, National Institute of Technology, Silchar. Then he is also having different license and certificates from the Dassault Systems like Certified SolidWorks Simulation Expert, then Elite Application Engineer, then Certified SolidWorks Expert like this. And again, he is also acting as a director for Shivanirmiti Engineering Private Limited. So he is a expert in simulation, then doing consultancy work also, and he is director of one of the Shivanirmiti Engineering Private Limited, so we can call him as entrepreneur. So a very good combination, and sir is having very passionate about the simulations, that is design, analysis, and all the related things by using SolidWorks, CATIA, and ANSYS. So we are having such an eminent personality. So I welcome you, sir, Shivkant sir, for this session as the head of department from Department of Mechanical Engineering, Swedish College of Engineering, Pandharpur. And without taking much more time, I request Honorable Mr. Shivkant Tilekar sir to take the charge and to guide our students in terms of this simulation and SolidWorks and ANSYS. Thank you, sir. Shivkant
Yes,
sir.
Yeah. Thank you, Sandeep sir, for those warm welcome. Just a question before. Can I start sharing my screen right away?
Yes, sir.
Yeah. Okay. I think I need a permission from your side.
No,
sir.
already I have given permission, sir.
Yeah, got it.
Now.
Sure. So I hope my screen is visible.
Yes, yes, sir.
Great. So good morning and welcome to this new year. My name is Shivkant. I'll be your presenter today. And this session will be about a basic introduction about the finite element analysis using SolidWorks. And without any ado, let me just have my wishes to all of you. Wish you happy new year and have a great new year ahead. So let's dive in and see what we can do in the finite element analysis and how we can make use of that finite element techniques to our practical gains. So let's see. First but not least, that's me. My name is Shivkant. Just as Sandeep sir told, I am working as a passionate simulation specialist in Best Engineering Aids and Consultancies Private Limited. And so in short, this is my profile, and I'll be your host for guiding you to about the basic introduction about finite element analysis. So let me just go ahead and see what engineering problems we solve in our engineering curriculums. So my basic start point is like this one. So we, as an engineer, you must have solved these problems throughout your engineering careers. Like in the engineering mechanics, you must have solved the problems of the truss design, the pulley and ropes. You must have remembered these things from somewhere. rigid body motions where the velocity needs to be found out. We made use of Newton's law of motions, etc. I think one of your mic is on unmute. I request you to kindly mute that mic, please. Thank you. So as I was saying, we must have solved these type of problems in our day-to-day engineering activities, like block and break design. We must have encountered this in the third years. Vibration analysis must be part of your fourth year curriculums and etc. Heat transfer problems, thermodynamics and etc. Any theory of machines, quick return mechanisms and etc. So typically we solve these type of problem in our engineering curriculum, targeting different physics along with that. So you must have seen that we have applied different physics. So here engineering mechanics plays a very important role, where we have studied static and dynamics. Here also the mechanics of material, that is strength of material, plays very important role in this case. Also here we have studied about the vibration analysis, heat transfer and etc. So those different physics we have studied in bits and pieces. What we are trying to achieve here is we are trying to achieve all this physics combined together to have an application to a particular product design, so that that product efficiency and the performance will increase, and safety also will increase along with that. So that's our main motto behind having this basic engineering problems to solve. And prior to FEA, while we solve these problems, we have the limitations because we are using the hand calculations to solve it, and a physical testing to test these examples in the labs and etc. So as you can see towards the right hand side image, we have this beam tested in the lab. As you can see, there's a heavy investment in the laboratory, heavy investment in the lab equipments, manpower, prototyping, and etc. So definitely engineers have thought out some way to bring this down. And the another limitations to it is they provide very limited
Siddesh sir, what happened?
I think Shivkant sir left. Maybe
Speaker side, I think.
okay.
Okay, he will join.
I
No
think
problem.
yes.
Hello.
Yes, sir, continue.
Shivkant sir, please continue. And please share your screen once again.
I think Shivkant sir is not in meeting.
Yeah, I think there was a slight technical glitch. Hello.
Oh, okay, sir. Okay,
You
sir.
can
Continue,
share.
please.
You are audible. You can share your screen and continue.
Sure. I think I have introduced these problems first, right? Hello.
Yeah, sir. Yeah, sir. Okay.
Okay, sure. So we've solved this type of problem in our engineering curriculums and focused more on how to get the solutions directly using the hand calculations. So before the finite element analysis came, engineers used to rely on the hand calculations and the physical testings. So these methods ensure that design performance is met, but there's a slight problem in that thing. That is, they give a very limited insight to the product performance. And also, as you can see towards the right hand side, it also comes with the heavy cost. That is, we have to build a prototype, spend on the expensive lab equipments, spend on the manpower, and most of the times, when we try to optimize the design, it's always a matter of guesswork, trial and error, and approach to the design. Yes. So in by means, you can see the hand calculations are available to the limited number of geometries. Only standard geometries will be calculated by hand, like simply supported beams, as you can say. I'm just taking an example of beam because that's a common ground for all of us. We must have studied this. And you can see there is a very handpicks of geometry that we have analyzed using our hand calculations. But typically, in our industrial applications, the product became very complex. It's not just a matter of simple geometry, simple calculations here. There are different cross sections to the geometries, not a single regular cross sections and etc. As you can see in the latter images, there are different geometries are there. I just picked out some of the geometries for us, which is, let's say, you can see the connecting rods, the pipe lifter assembly. This head is made in the CAD software. So as you can see, the geometry is very complex to analyze. And when we try to fit our hand calculations to it, it might have some limitations and some small insight into the product, but not the good insight into the product. So this will ultimately increase the product design cycle time when we only do the hand calculations and etc. So as you must have known, let's say in the 1980s, the car we used to have a very slow launch cycle for the cars here. So I think that time the ambassador car was there. So only design change that they made during that car is like they have improved some of the seating arrangements in the latter years. So as you can see, the cycle time at the time was around 8 to 10 years to improve the car to in such extent. But nowadays you can see the car can come to the market at a much faster rate. Within 3 to 5 years of the announcement, the car you can usually see in the market good to go, and it can last a very long time. So that's the improvement, as you can see, because of the implementation of the finite element analysis. That's the improvement have been done in the market. So typically the finite element analysis, let me introduce about it. The finite element analysis is the simulation of any given physical phenomenon using a numerical technique. It's called finite element method. So basically we are doing mathematics calculations only, but with the numerical techniques. You must have studied about the numerical techniques. I can list a few, like Newton-Raphson. It's a very popular one. Harangi-Kutta, it's also very popular. So those kind of numerical techniques have been used, secant method, Lagrange's method, and etc. etc. So those numerical techniques have been used to solve the equations that is very important for us. In this case, the equation of beams and etc. So by using this method, we are solving our engineering problems, and we are solving it with the help of a computer. So obviously, the machines can do a better job by number crunching than the humans. So we can develop a program, and we also we can have a look at the commercial softwares available in the market, which can do this number crunching for us and give us the final output at the end. So with the help of that, you can test your product design before it can go to the manufacturing. And that is really important for new engineers to know that you shall not always be rely on the hand calculations. You must learn and gain an insight about these products available in the market. That will definitely give the boost to your careers. So you can test the design against a broad range of parameters during this design process. You can have like a durability test, static test, dynamic response, vibration test, motion analysis, heat transfer, and etc. There are different physics we can solve, and depending on different applications that we are encountering. And engineers usually use this finite element software to reduce the number of prototypes to be tested. Obviously, for the statutory purposes, the prototype must be tested. That is in the statutory laws. But instead of starting from the scratch and ground level, what we can do is we can actually start from an educated guess. by improving the design first directly inside the computer-aided environment, and then after testing it in the computers, we can test one or two prototype, which is at the final stages, and we can still have the definite performance met as per our requirements. So this will definitely drives our design cycle faster. So it would be very interesting to know how the finite element works. So as you can see, I have taken a very simple example to get you know about how the finite element works. I am taking simple example like you can see, there's a road connecting to my mailbox from my home, and you can see I need to measure the distance. So I'm taking a very practical example with the help of this finite element. I need to measure the length of this curved path using the only equipment that I have right now, which is a measuring stick here. As you can see, there's scale here. So when I try to measure this distance, what I can do is I can place a different scales. I can mark the spots. I can have the spot mark with a different scales, and you can see I can approximate this path, and I can map this geometry with the help of the only tool that I have in my hand, which is scale. So by mapping this geometry, I am ensuring whatever I want to find out, in this case the distance, is there. Obviously, when I take a smaller scale, the much accurate distance can be measured, but it also comes with the cost that I have to invest more time in this problem actually. So the same funda is applied to the finite element analysis. We generally divide this geometry into different small elements, and we get the geometry and we find out the unknowns at the last of it. So the curve path here is approximated by the straight segments, and we use this using the measuring sticks. So in the finite element, generally what happens is we have a CAD model with us, which is 3D computer aided model, and we find out the final values, that is stress resistance and etc. But it goes through a process. It's not as simple as taking a sticks and measuring it. But we have to encounter some of the engineering calculations which we have done in our engineering, and we can take those calculations in the background, give it to the computer, and computer will solve it for us and give it back. So generally we have to feed a CAD geometry to it. As you can see, the CAD geometry is a basic step to feed to the finite element solvers. Then what we can do is, in order to have this geometry solved, we can do some approximations, some assumptions to be made, and some geometries need to be simplified. So those steps come very first. So you can see the geometry is simplified in this case. And then we need to form a mathematical model. So how we can form a mathematical model, we can see in the later slides. But let's understand this, how the finite element is working here. So the mathematical model is built on what type of analysis there, what are the material properties are there, how this structure is rigidly connected to the other structures, what are the loads, what are the boundary conditions are there. So by feeding these informations to the mathematical model there, what we are doing is we are actually building a real life environment, but through the glasses of the mathematics. And we are asking the computers to solve it for us. And it can be done. It can be definitely done. So just like we map our geometry with the help of the sticks, we map the geometry with the help of some elements. So there are different elements. I'll introduce them in the later slides. So those elements will map the geometry at significant points. So those points are called nodes. And after mapping the geometry on those nodes, the solver, numerical solver, which make use of this numerical techniques, will solve this for us, and we'll get the final results of our requirements. So in nutshell, this will work like this. So in order to map this geometry, we have a different elements at our disposal. As you can see, there are different elements are there. Like we have the tetrahedral solid element shown in front of you. So this is tetrahedral solid element, which comes into the first order and the higher orders also. So we make use of this tetrahedral elements to fit this into the geometry and find out the important unknowns for us. Usually this can be a displacement, it can be stresses, it can be the strains and etc. We find these unknowns at the significant points which are important for us. And by combining all this, we map the geometry and get the final results in the geometry. It's not the only thing that we can do with the it's not only that we can use these the solid elements. There are shell elements also, which is very, very helpful to in order to map the very thin geometries where if we try to fit a solid element in this case, there are a lot of elements we have to invest and a lot of calculations times we have to do. But this can be greatly simplified making use of the shell elements in this case, which is also one of the mapping instrument that we have inside the finite element. Next thing, let's say we have a support structures and etc. We can make use of a beam element, which is a 1D elements, and we can map such geometries into place. So as you can see, we have different scales in order to map the geometry and solve a problem to get the final insight. So if I summarize this, the mesh is an approximate representation of the CAD geometries using those tetrahedrals, triangles, and beams, elements, etc. The elements are those tetrahedrons, triangles, and etc. Nodes are a point where different elements are joined together, and usually the location where the unknown values are found out or approximated. So we have seen how the finite element works. So let's have some glimpse about how is the mathematics is working behind this finite element. So let's consider this one-dimensional problems. You must have solved this problem many times in our engineering. Let's take a simple rod. I applied some force to it. We have its length L, and when we apply a force, there will be a change in length, which is delta L. It's represented like that. So usually the stress produced in the finite element, stress produced in this rod is like sigma, which is force upon the cross-sectional area. And when we apply the Young's modulus, so stress is proportional to the strain, and the modulus of elasticity is obviously the constant. When we are talking about the linear region of the stress strain curve, so when where in this case the strain is delta L upon L, which is change in length upon the original length. Now, if you have any problems in between, then kindly let me know, because I am seeing some of the screens online here. Okay, anyway. Sure. So the Young modulus is representing the stresses proportional to the strain and etc. So after rearranging all these terms in order to fit the force is equal to some unknown, then what we can do, we can achieve this expression. So when we resubstitute these terms into one another, and you can see the force can be equal to some E upon L into the change in length. So in order to, we have solved this problem by using the hand calculations that are here. But computer doesn't understand direct solving methods. It have to rely on some numbers and numerical calculations behind it. So in order to understand a computer how to solve this problem, we can have an approximate system to build it. So what we can do is we can approximate this rod under tension system with the help of a simple system, a spring. So where you can see the force is applied to these ends, and it has some stiffness to it. So the equivalent system of the spring with the stiffness can be told as the force is equal to some stiffness into the change in length of this one. So when we approximate these two equations, you can see the stiffness, which is K in this case, is obviously is equal to EA upon L. So what we can conclude from this is the stiffness is mainly dependent on the material properties which is the modulus of elasticity in this case, and the geometrical parameters, which is area and length and etc. So these are the main two contributors to the stiffness, and we can make use of that into the finite element. So with the help of finite element, we can form a global matrix of the stiffness, and where we can have the nodal forces acting, nodal displacement, and this global stiffness matrix can be created for complicated geometries as well, not the simple geometries. As I have shown you already, we can form the complicated geometry into the finite elements with the help of those triangle, tetrahedron, triangles, and etc. And we're trying to solve this mathematical equations onto those nodes and find out the results at the end. So this expression, in these expressions, usually forces are unknown entities. So forces are known entities, and the displacement are usually the unknown entities. So it can be vice versa, of course. If we know the displacement, we can also predict the forces, vice versa. But usually the displacements are unknown entities. So when we know this kind of stuff for the one-dimensional problem, we can extend our scope of the problems to three-dimensional as well. So in the three-dimensional problems, the problem become complex with the 3D because it introduces more number of material constants for the analysis. As you can see, the bigger stiffness matrix right in front of you, the force is equal to K's U, which is expressed as a 6x6 matrix in this case for the stiffness. And there are different unknowns here. Like you must have studied this into your engineering curriculums. Like there are material constants, the Poisson's ratio, modulus of elasticity, etc., etc. Those unknowns are different for each directions. When we are assuming the material is not linear elastic and isotropic. So when we talk about composite material, this matrix becomes almost unknown of 22 constants, and we have to solve this complicated problem inside the computer. So, and these material parameters definitely be found out experimentally only. There's no other way. And with the theories, we link this to the finite element, and we can finally predict the material failures. So this is what going on inside the finite element softwares. You don't have to worry that much about it. I just shown it to have the better understanding of the subject. And with the help of this, we can solve different physics. So just as I told, we can target linear static, fatigue, the frequency, which is a natural frequency analysis, and etc. Also, we can optimize our structures. We do the thermal analysis, nonlinear analysis, and the linear dynamic, which is a vibration analysis in this case. So different physics can be targeted and solved using these techniques, which is going on in the background. So in order to demonstrate all this, let me take a very simple examples and find out the correlation between the hand calculations and the finite element. We obviously done this hand calculations with us. You can see, let me just number of these hand calculations for us. So in order to demonstrate this, let me take a simple example of a beam force. And you can see, let me just have this simple example of beam force here. So you can see towards the right hand side, I am taking an example of a simply supported beam with the UDL. And this UDL, I have assumed some value of 2000 Newton meter, and the length of this beam is 1 meter. I assume those values in order to solve this problem numerically. So when I go ahead and look for the shear force diagram, you can see the shear force diagram right away in this case, and which is the maximum shear force coming onto this these ends, obviously at these ends, and the value is, which is WL upon 2, which is 1000 Newton at each end. Also, the maximum bending moment, it's WL square by 8, And when we compute this value by substituting these assumed values of numerics values here, we can see the reaction forces or the shear forces in this case are 1000 Newton, and the maximum bending moment is 250 Newton meter. So let me take the same problem inside the SOLIDWORKS simulation and show it to you. So I think my SOLIDWORKS screen is visible to you.
Yes, sir. No problem.
Yeah. Okay. So I'm taking a very simple example of a beam here. So as you can see, I'm in the 3D CAD environment of the SOLIDWORKS. I'm taking a simple geometry for now, and I'm going to apply these problem conditions to this one. So as I told, different physics can be solved. Those can be selected from this end. I have already gone ahead and selected a few of these things. I have set up the problem for us just as we know. I have set up these boundary conditions, applied a force of 2000 Newton meter in this negative y direction. And when we solve this problem, as you can see, it is behaving exactly as we can see. Don't misunderstood with this circular conversion of this. It is just a graphical representation. I can easily fix this. I can render the beam profile. Oh, sorry. Yeah. So that was our previous geometry. As you can see, this displacement is around 1.873 millimeters, and it is magnified almost 53 times. So that's where we can see the difference. Otherwise, if we see this for the true scales, we just see the flash of colors, because the displacement is very small in this case. In order to get a good idea about it, we can scale this displacement and see how this displacement is going on. So when we set it to the automatic scale, which is 53 times magnified scale, we can see the displacement is fairly in this one. So setting up a problem inside this one is very easy. SolidWorks simulation is a single window integration tool. That means your CAD model and your simulations work along with each other, and where we can find out different unknowns with the help of this. So you can see the stresses values can be found out, and also we can find out the shear force and bending moment diagrams here. So you can see clearly how we can find out the shear force and the bending moment diagrams in this case. So let me just come back to the PPT and conclude this and there. So generally, whenever we try to find out these problems and whenever we find out these unknowns, we must have to assume some of the coordinate system. The beam have its own coordinate system, which is you can see the red axis, which is axial direction 1 and direction 2. So when we take a list of these beam forces, we can have the list of the forces displayed right away over here. And after running the beam analysis, we can extract this list of the forces. And when we compare this with the hand calculations, so you can clearly see when I point out the extreme values at the ends, which is the beam force. So we can see the shear force coming onto these ends are clearly the same value of 1000 Newton as we have computed from the hand calculations. Also, we have the values of the bending moment to be extracted. So you can see at these ends, bending moments are very negligible. But in this case, when we take the extreme values for the bending moment, so you can see the extreme value of the bending moment is also 250 Newton meter, which is an exact match with our hand calculations. So as you can see, the graphical representation also matches the same thing and give the same values here. Same is true for the bending moment equations. So by now, I must have given a very good idea about how this technique works and how it is correlated with the finite element analysis and how the hand calculations are correlated with the FEM. So let's dive in and see a few of the applications that are solved using this technique. So the first thing I want to introduce about this basic tank containers. This is one of the project that I solved for my customer. So this is the tank container, basic simple problem that we have. I can definitely show you the much complex problem, but let's not go into that deep dive right now. Okay, let me just introduce about this small tank container problems. So here you can see I have to analyze this structure. So I have taken the structure like this one, which have the vessel here, and this structure is made inside the SolidWorks, of course, and you can see there's a lifting hook here. So my objective is to calculate a factor of safety of the structure if it is filled with the liquid, and whenever it is lifted by the lifting lug from the transportation, it should not fail. So there will be hooks here, and when we lift this and place it onto, let's say, a railway wagon or let's say a truck, then in that case this should not fail. So that's my basic objective behind this study. So I'm going to make use of the basic things that I've shown, like solid elements, sheet elements, shell elements, beam elements, and etc. And I have a combination of these elements and solve the problem for us. This is basically a linear static analysis. There are underlying assumptions to it, like response is proportional to the applied load. We are only talking about the responses which are very, very small and etc. compared to the geometry of the model. Also, the material is linearly elastic. There's it will not obviously cross the yield point. That is also one of my assumption, and the loads are also the static one. And obviously we are going to lift it at a very, very slow speed, not sudden jerk is to be given to this lifting portion. So that is my basic assumptions in order to evaluate this under this linear static analysis. So let me just go to the SolidWorks and show you that example to you. So I have this example shown it to you. Let me just take this example. Yeah. So you can see the frame have been made inside the SolidWorks along with this pressure vessel tank. And this assembly have been made inside the SolidWorks also environment. So in order to evaluate the structure only, we do not need to take this also vessel into the account. What we can do is, with the help of some techniques, we can replicate the effects of this weight carrying this vessel carrying the liquid weight to these members. Because they are rigidly welded together, I can directly transfer this weight to it. So in order to do that, what I can do is I can take a center of mass of this one and take a location of this and place a coordinate system there, so that I can replicate the effect of the mass to that main structure here. So when I set up the simulation study, in this case, you can see I can replicate the simple mass of this to the different coordinates, different faces here. Those are rigidly connected to it, and I can enter the value of the definite forces that is there. Also, the self weight can also be taken into the account by just turning on the gravity. So once everything is in the order, so you can see in order to replicate the effect of this hooks, I can take a fixture, which is in this case the fixed geometry fixture. I'm assuming there's no relative motion between the hooks and this lifting lug. So under these assumptions, I am lifting this. So when I solve this problem finally, so you can see this will be behaving exactly as we can predict. So when I apply the displacement for this one, so you can see it has to be come like this likewise, which is exactly behaving as our real life predictions. And of course, we can rely on these calculations as we have seen beforehand how those are very, very correlated with our hand calculations too. So next thing you can see, we can obviously check for the stresses in the equipments. As you can see, I can point out the stresses firstly for the solids and shells. I can also point out the stresses for the beams by just having the stresses for the beams. And of course, we can browse with the different variety of the stresses, like principal stresses, von Mises stresses, the normal stresses, shear stresses, and etc.
Sir, you are offline. Chetan sir. Chetan sir, please check. Chetan sir. Chetan sir. Chetan sir.
Sir, please share your screen. Presentation is not visible.
Shivkant sir.
Yeah, please call him and tell him. Amit sir, please call our honorable speaker and tell him to join again.
Hello.
Please call our speaker and tell him to join again.
Okay.
Can I request the coordinator to call the speaker and confirm what happened?
Hello.
Yes, sir. You are audible now.
Shivkant sir,
please
you are
proceed.
audible. Just
Great.
please reshare the screen and then again the session will be started.
Yes, sir.
Sure.
Now it is visible, sir.
Visible and audible. Okay. Continue, sir.
Great. So as I was saying, we can browse for the different stresses as per our choice. It can be von Mises stresses, it can be the principal stresses, and etc. And check the stress state of that particular components and that particular assembly of our choice. So with the help of this, I can directly browse here and create some of the stress plots. Also, the factor of safety of the components can also be seen, depending on the stress. So as expected, the minimum factor of safety of this equipment is around 1.8 since we have seen the stress rate. And we can definitely point out the critical areas in the design that the lifting lugs are critically having the critical areas. And definitely we can, as a designer, so that our definite factor of safety requirements will be met. So that's how we can proceed further with the design and development cycles. So let me just take back to the PPT and take one more example on the same thing. You can see in this example, we can see wherever the construction is going on. This is an example of the scaffolding. So they usually take the pipes and they mount some of the pipes one on another, and you can see they have the this wooden plank mounted onto it, and some persons will climb onto it along with the equipments and etc. So as you can see, it is very important to analyze such a kind of geometries as well, because the persons working are their lives directly dependent on this kind of equipments. Otherwise, there will be an injuries and etc. So in order to simulate this scaffolding, let me take one of also the basic example here, where this structure is subjected to the 3,500 Newton forces and 1,650 Newton force combined with the gravity forces. As you can see, there are two persons standing here along with the equipments and etc. Those will make this kind of loading structures here. So when we have this model also inside the CAD, so you can see the same techniques can be used in order to do this geometry analyzed. We can also go ahead and get the help of the simulations here. I can set up a new simulation study right over here. And after setting the simulation study, I can assign first, I can map the geometry with the different elements. As you can see, it's already been mapped for us because I have solved this problem. And I can assign the different material properties to it. There are a variety of material properties available in SOLIDWORKS environment, and those material constant that I was talking about, those are involved here in this material property, where the required constants are elastic modulus, Poisson's ratio, density, yield strength, and etc. Those will be used in this analysis. And we can also have how this component connected to one another. There can be a welding, there can be a bolted connections, and etc. Those can also be simulated using this environment with the help of this connection. You can see there can be a bolt connectors, spring connectors, weld connectors, and etc. And the loading conditions have been applied over here. In order to simplify the analysis, we do not have to take the effect of the plank here. So that weight along with the equipment's weight and etc. can be applied directly to this framework which is there. And also the self weight of this frame can also be taken into the account. So finally, when we have this geometry analyzed, we can directly point here and see how the geometry is behaving under these loading conditions. So you can see the maximum displacement obviously occurring at the middle portion, which is almost 13.77 Newton, 13.77 millimeters. And when we check the stress state and the factor of safety of it, we can have a better idea about how this equipment is going to behave in our real world. Finally, you can see this equipment is actually 1.5 times safer than the applied loads. So we can conclude these things based on these examples. So let me just quickly go back to the PPT and explain furthermore. Okay, here I'm going to take an example of the buckling. So you all know the buckling is definitely going to occur whenever there are compressive loads, and where we have very long and thin members or the slender members along with this. So typically, the buckling is a phenomenon occurring whenever there are compressive loads are involved, and the long and slender members are there. So you can see variety of buckling failures can occur. I have taken this buckling example and studied it in the lab, and correlated this in one of the finite element software which is available with us, which is Abacus. So in this case, I'm going to show you the real examples. I have done this work along with my friend. So here you can see this. In order to study the buckling, first the equipment have been mounted onto the testing equipment, and the compressive loading have been applied. So obviously the material property is known to us. So whenever you can see whenever the equipment progresses, so you can see how this buckling is going to occur inside this one. And this actually shows us, okay, this is very, very satisfying result because we are intending to have this result. And we can obviously see, because we have hidden the camera here, how this phenomenon is going to occur from the inside in order to study this. So you can see clearly how the failure of the material is going to occur. So when I take a cross section of it after cutting it with the help of milling machines, so you can clearly see how this buckling modes have been taken effects into this. And after this, I studied this with the, as I said, the abacus, simile abacus technology. And when I set up the same problem inside the abacus, after this, when I go to the results after defining all the boundary conditions and etc., we can clearly see the results. Likewise, we can browse the results. Of course, we can browse for the animation video also, just as I said earlier. And we can have even one-to-one comparison between the practical testing as well as the simulation testing that is there. So as you can clearly see how it is greatly approximated towards the real life environment. Definitely, if I take one-on-one, when I take a cross-sectional animation here, so you can clearly see the buckling is going to occur at which points and etc., which is highly resembled with the practical testing. So let me have side-by-side comparisons to it. So likewise, we can clearly see how this is going to occur. And as I said, it have a great resemblance with the hand calculations as well as the practical testing. Let me share some light on a few of the more examples where you can also solve the rigid body dynamics and the FA combined. So here, the task was to design a new suspension system using the SOLIDWORKS. So here the conventional system involved this rod and etc. You can see you must have used this two-wheeler conventional system. Here the challenge was to design the new spring and damper system along with the tie rod in order to guide this wheel. Also have this shock absorbed in the this suspension systems. So what we can do is we can create this geometry inside the SOLIDWORKS, and we can also create the virtual testing rig inside this one. So in order to create this virtual testing rig, I have simulated one of the testing wheels here, and with the help of this motion study, I can go ahead and set up the rigid body motion model. I can assign the definite speed to this ground wheel here, and also some of the steering forces or steering actions while we are driving at this particular speed. The steering action also can also be specified here. This artificial spring and dampers is specified. So we can obviously extract the few meaningful results like displacement, velocity, accelerations to find out good damper combinations and damper and spring combinations to it. And we can have multiple goes at this inside the simulated environment. So when we choose a particular damper system for us, we can further go ahead and take the study to the next level, and we can set up the same problem inside by extracting the forces directly here. So you can see the maximum forces coming onto this joint can be extracted using this rigid body motion analysis. And once we have this rigid body motion analysis result extracted, we can apply this to the finite element analysis, and we can compute how is the factor of safety is there for this rod, whether it is going to sustain under these loading conditions and or not. If we are seeing that, okay, factor of safety is around 4.4 in this case, and which needs to be above 5, and resultant displacement should be less somewhat, we can think of a design change in this case. We can go to the SOLIDWORKS environment once again, link this, change it to very stiffer material like alloy steel, and you can clearly see the displacement will come down from 5.3 mm to the 4.3 mm in this case, which is a huge change for us inside this one. So likewise, we can go here with the motion study along with the finite element analysis. Here's another example based on the same funda. The virtual testing rig is tested for this rescue spreader equipment, and you can see we can simulate entire time cycle along with this. How these forces are varying and how the stresses are varying along with the time can also be specified during this virtual testing conditions. So in nutshell, motion analysis will give it the benefits of finding out the contact forces. We can transfer the loads from the motion to the simulation. We can also study the dynamic effects of the loads onto this one. From now onwards, let me just quickly introduce about what type of physics we can solve. It's already established how effectively we can solve it. Let me introduce the more number of physics here. We can also solve the natural frequency analysis, where we can predict the natural frequencies of the objects. So as you already know, it is important to predict the natural frequency of the object, because when it is coincide with the operating frequency, the resonance will occur and there will be an excessive shaking or the displacement of the components, which may hamper the equipments or produce more noise. So in order to have this effect reduced, what we can do is we can design an equipment in such a way that it will be away from our operating frequency range. Our natural frequency should be away from the operating frequency range, and that natural frequency can be found out using this frequency study. We can also solve the nonlinear problems, where the material nonlinearity, contact nonlinearity, and geometrical nonlinearity comes into play. Obviously, nonlinear material like hyperelastic material like rubbers and etc. So those hyperelastic materials can be solved in this nonlinear problems. Plastics can also be solved in the nonlinear problems. There's a considerable slidings in this case that can be also be solved using this nonlinear static as well as dynamic testing. So as long as you can see, this is the explicit nonlinear dynamic solving, where the testing have been done using one of the equipments here. Also, it can be solved in the 2D environment as well. So the same results can be replicated along with 360 degrees lines. And also, whenever there are complicated buckling problems, nonlinear bucklings are there. Obviously, the previous example, practical example that I've shown was the example of the nonlinear buckling. So those nonlinear buckling can also be solved using this type of finite element methods. So in conclusion, the plastics, rubber products can be analyzed for the large displacement. Also, material strength variation with respect to temperature, which can be creep, and those effects can also be studied inside the finite element analysis. Okay, it's not only the nonlinear, but also we can study about the vibration effects, how the vibration is going to affect our product, and we can prevent this vibration effect by adding some of the more stiffnesses and the conditions suited to our need. So you can see we can study the dynamic time history curve. Where we solve entire time domain. Also, the harmonic analysis of the structures can also be done. Also, the random vibration analysis. So let's say where this equipment is placed on the car roof and where the electronic control units are there. So let's assume this is the electronic control unit of the car. So it is not only subjected to standard vibrations, but it's subjected to very random vibrations which is coming from the road. So in this case, it has to be tested to our requirements in order to satisfy the definite codes from these standards. So when we can study this response of the structure due to this random vibration analysis. So in the dynamic studies, we can study the dynamic loads. We can simulate a shaker test. Even if you have the earthquake curves, then those earthquake curves can also be earthquake simulations can also be simulated for the huge structures. And of course, last but not least, the composite materials can also be simulated using this one. So where we can predict the individual layer failures and laminate strength for the different fiber orientations. And obviously, these applications have for the storage tanks, automotives, aerospace, etc. So typically, what happened when we use a finite element is, as an end user, whenever we are trying to do the design, we develop a concept first, we do a detailed product design later, and then comes the part of the validation and prototyping. And this process can be accelerated using the finite element method, like this one. We can do this product validation along with the product design. So the latter stage can be avoided, and expensive prototyping cost can be avoided, and etc. So this will definitely help as a business owner, as a business persons to make the design decision faster. And this is where your knowledge comes into the picture. As an engineer, you should always be aware how we can speed up our processes by not compromising the quality of our engineering calculations. And this is the tool for you. This is the finite element tool for you from my side. So as long as you're not asleep, I request you all to have some question for me, and I'll be happy to answer those questions for you. Hello.
Sir, we have heard about finite element methods also. So can you throw some light on how the FEA differs from FEM in short?
See, finite element analysis, the finite element method, it's a mathematical term for the finite element analysis. Actually, in the background, it is a finite element method only. Okay, but we are doing it for the analyzing the geometries which are important for us. That's where the analysis comes into the play.
Hello, sir.
Yeah.
Can we do here 1D simulations, like what softwares like GT Suite they do? 1D simulations of whole system. That way, can we do in this?
Yeah, there are some softwares where can do one-dimensional analysis. Yeah, but what the method that I've shown you right now was mainly focused on the three-dimensional analysis. Yeah, there are some softwares which make use of the one-dimensional analysis as well.
Yes, students.
Okay, sir, for static analysis, yes, sir. Runga sir, you can continue.
No, I was saying, students, if you have any questions, go ahead and ask. So meanwhile, sir, Chetan sir, you can ask.
Okay, sir. Thank you. Okay, sir. Sir, for static analysis, which software is best suitable? I can just ANSYS or Abacus.
Yeah. Actually, that is a very common question people usually ask. Which software is more suitable for us? Of course, the ANSYS are a very famous name. They have done a lot of experiments, a lot of benchmarks throughout the industries and through educational institute. See, what I can tell you is this. Let's say I have this calculator with me, and I type 100 plus 100 here. And when you open up your phone calculator, you type 100 plus 100 there. Will you get a different results?
No, sir.
Why? Because the mathematics behind it is the same.
Yes.
What we have to take care here is, I actually did the practical comparisons also between these two softwares. So here, what I did is I take the same mesh model created inside one mesher. I feed the same mesh model to the Abacus. I feed the same mesh model to the ANSYS, applying the same boundary conditions, and you can clearly see there is absolutely no difference between the results. But only what we can say here is at the least possibility, some solvers like Abacus are more pronounced or more renowned in the area of solving the nonlinear analysis problems. And ANSYS is very good solver, generic solver for that purpose. Even Abacus is very renowned solver. But on the mathematical level, there's no difference between the software, and you can rely on all those codes very well.
Okay, sir. Thank you. One question from the student, I think Prem Sawan. I'm not able to use simulation in my SolidWorks. Prem Sawan, you can just unmute yourself and ask question to sir directly. Hello, Prem Sawan.
Okay, by the time I will
Okay.
ask.
Yes, sir. Yes, sir. Continue.
The modeling part, can we do it here itself, or is it necessary that we should prepare the model in some another modeling software and then import it here?
Yeah, either is possible, sir. If you have imported a model with you in SolidWorks, in Abacus, in any software, you can set up these simulation projects. It's the advantage to model in the same software is if you want to make a design change and rerun the analysis, that is very fast when you have the model done in the same software and analysis done in the same software.
Yeah.
Like
Sure.
this is a CAD integrated solutions that I have shown right now.
Okay.
So let's say if I want to make any changes here, I can directly go to the CAD window. I can make the changes, come back, rerun the analysis.
Correct.
So that's the
Correct.
faster time you will have when you're trying to solve inside the same interface.
Correct. Okay, sir. Thank you.
Okay, so I think question is over from all the sides. So again, I request Professor Yasvi Jadhav sir for the last part. Vote of thanks. Jadhav sir, please.
Okay. Okay. Thank you, Chetan sir, for giving me an opportunity to say thanks to such a renowned person. Okay. I thank Mr. Shivakant sir to speak on this particular topic, Introduction to Finite Element Analysis using SolidWorks, wherein he basically give an insight from the beginner's point of view. So nicely gave the overview. So he started from the basics. He correlated the physical problems, actual practical problems, because he is having a wonderful experience, practical experience from working with the industry. He also told why FEA is required to be used, wherein he said the then related to different applications like containers, failure analysis, and so many things, wherein he brought in front of us the strength of this particular software, wherein in this particular era of skills, it becomes very important, and that too when students tend to have a fear in their mind regarding going for studying or learning this particular softwares, because they wonder what is that, how it is working, they don't know anything, and something like that. So he wonderfully and very nicely simplified the things and told what is the physics behind the working of this software, how mathematical model is being created in this particular software, what type of problems can be solved, like vibration analysis or frequency analysis, etc. And in all, it was a very nice journey, even though it was a very short of 1 hour only, but in a very short span of 1 hour, he has introduced this particular software very nicely to students. I thank from the Sweris College of Engineering and students of Sweris College of Engineering, Shivkumar sir. Once again, I thanks a lot. And over to you, Chetan sir.
Thank you, sir.
Okay, so Dr. Wangekar, sir. Hello.
Okay, so I am very much thankful to Shivkant sir, and from the Department of Mechanical Engineering on the first day itself. Very great session. Our students are fortunate to have Shivkant sir session related to SolidWorks and simulation. So I express my gratitude, sincere gratitude towards Shivkant sir for sparing his time and guiding, sharing your valuable views and guidance to our students. And now I wish you all the students also wish you a very happy, prosperous new year, which will come with many of the great achievements in your curriculum. And I am once again thankful to Shivkant sir. Okay, thank you.
You're welcome, sir. Thank you.
Okay, so we can conclude here. So thank you very much, and wish you all the very happy new year, all of you.
Yes.
Thank you
I wish
very
you
much.
happy new year to all of you.